In this video, I want to give a quick overview of what we learned about analyzing RC and RL circuits. So imagine I have the following situation. I have a circuit with one capacitor, and at time equal to 0, this switch is flipped from position 1 to position 2. So this is an event, and what I'm interested in is what is the time evolution of a voltage or current in my system as a result of this event, right? So for example, this I1. Now let's look a little bit closer at these particular events that can occur. So the event could be a switch flipping, and as a result, the circuit this becomes completely different. You could also have a situation where I'm, for example, connecting a capacitor into a circuit by flipping a switch, or I could just have a change in time of a voltage or current source. So then this jump in time is the event that I'm talking about. And what do I know is when I look at the voltage or current in my system as a result of any of these events, I'm going to get a time evolution that looks like this, or in general has a decaying exponential shape. And so the goal is to calculate this curve. And a key thing that we're going to use to do this is the realization that the capacitor actually can relate what the situation is before the event to what the situation is after the event. The capacitor has memory, and that's really crucial here when we're going to analyze these types of circuits. If this were a circuit with an inductor, it would be the inductor current that remembers and basically relates what's happening before the event to what's happening after the event. Okay, so how do we analyze? Well, we first start by looking at the situation before the event. So before, in this case, this switch is flipped, and in that case my circuit looks like this, and I need to calculate two things. One is that voltage or current that I'm interested in, but also what's the capacitor voltage before the event. Now, before the event, I'm going to assume that the system has been stable for a while, and so that nothing is changing anymore. And so in that case, the capacitor behaves as an open circuit. Everything has settled, everything is at DC, and so the capacitor behaves as an open circuit, and I can just analyze this system here, and I can do this using the analysis techniques that I'm very familiar with. KCL, KVL, nodal analysis, mesh analysis, source transformations, whatever you want to use. So I can calculate my current or voltage of interest, but also the voltage here over the open where my capacitor used to be. One quick note is that we can calculate the voltage over the capacitor, but sometimes you're in a situation where you don't really have a circuit that is going to help you very much in calculating this value. For example, here in the second example, in that case somebody will need to give you the initial condition, right? So sometimes you will need to calculate it, what the voltage was over the capacitor before the event. Sometimes you will need to actually know, so somebody will need to give you, this is the initial voltage of my capacitor just before the event. Okay, what's next is right after the event. Well, right after the event, the switch has moved, and I know that my capacitor voltage is the same as what it was before the event. So I can use this. I can look at the capacitor voltage as a known quantity. So it's kind of as if it's behaving as a voltage source, but just at that point in time. And I can analyze my circuit, but now with my capacitor as a voltage source, and I can find my current or voltage of interest. And then next, I'm going to try to see, well, where are we going to end up? So what is the final value of my voltage or current? And in that case, when everything is settled, the capacitor is again an open circuit. And so I can use this circuit now to do my calculations. And in between, there's going to be a time evolution. And this time evolution will follow an equation like this. And I need to just calculate 3 parameters, a, b, and this time constant tau. To calculate tau, what we're going to do is we're going to look at my system and basically take out the capacitor, and what's left of my circuit I'm going to simplify into a Thevenin model. And once I have that, my Thevenin resistance can be used to calculate the time constant. So my time constant is my Thevenin resistance times my capacitor value. So how do I calculate this Thevenin resistance? Well, I take my system without a capacitor, and those are my 2 points A and B, and I want to find the Thevenin equivalent resistance between A and B. And I can do that by setting all my independent sources to 0 and just look for this Thevenin resistance. Now, this procedure is called looking for the resistance as seen by the capacitor. Okay, so this is how I calculate tau. Now, how do you calculate A and B? Well, I know 2 values. I know the value at t equal to infinity and at t equal to 0 right after the event. And so I can use that, plug it into the equation, and find A and B. And so this is a procedure to find the complete solution to the time evolution of a voltage or current in my system. So to summarize, you start off with looking at what does the system look like before the event, and my capacitor can be approximated or simplified to an open circuit. Then you look at right after the event, and in this case I know the capacitor voltage, it's the same as what it was before the event. Then I look at what happens when everything is settled, so at time equal to infinity, and the capacitor is again on open. And then finally, I am going to calculate my Thevenin equivalent resistance, so I can find the time constant and write my equation, and with the values I'll calculate it in 2 and 3, step 2 and 3, I can find A and B. Okay, so this was one procedure. An alternative approach is by actually writing the differential equation. So you could write a differential equation for my capacitor voltage, solve it, and then express any voltage or current in my system as a function of that capacitor voltage. So here I summarized both of these approaches, and the one we focused on here is this approach B, where you don't actually write a differential equation, but you just solve the system in different scenarios. Each one of them is fairly simple. The capacitor either is a voltage source or an open circuit, or you look at the Thevenin equivalent resistance. And we've done this now for capacitors. For inductors, it's very similar. Just for inductors, at DC, an inductor is a short, and what's remembered from before and after the event is basically the inductor current. That has to remain the same. Other than that, you follow the same procedure. So this is just a quick summary of how you can solve RC or RL circuits.